we're going to look at is called the differential formula for arc length. So we're going to suppose that we have a continuous curve. So suppose y equals f of x is continuous. So we have a definition from calculus for continuous, which means the limit on the left matches the limit on the right, matches the value for every single point inside of an interval. And that's great when you're trying to prove something's continuous. We need a continuous function here because if we're going to measure arc length, we don't want any breaks in the curve. So what we really don't want is something that would have like a vertical asymptote, which would give us an infinite arc length if we tried to go across an asymptote. So continuous for us really just means there's going to be no jumps in the graph, no vertical asymptotes we're going to integrate across. If your function is not continuous and you still want an arc length, you would basically break it up into sections that were continuous. Measure each of them individually, add them all together. That's how you would handle a non-continuous function. There's 3 pieces, you add up all the lengths of the 3 pieces. All right, so we're going to suppose we have a continuous function and the derivative is continuous on interval a, b. I don't really care about if it's continuous everywhere, but we want it to be continuous from a to b. So we're going to let s of x equal integral a to x square root 1 plus f prime of x squared. Ooh, it should be f prime of t squared. Don't want to use x all over the place. So we're just using a dummy variable t because we're already using x. So this is basically arc length from a up to x. This is going to be a continuous function by the fundamental theorem of calculus. F of x is continuous by fundamental theorem of calculus. So basically, if you got a continuous function and you add up the area under curve slowly, that area increases or decreases in a nice continuous way. And that's the part of the fundamental theorem of calculus that we're using here to say this is continuous. So this measures the length across the curve, which we saw before. Along the curve, y equals f of x. On the interval, what interval does this measure the length on? From what to what? You can definitely answer this question if you think about it. A to x. We better make sure x doesn't go past b, so you want to go outside of where you know you're continuous. Another way you could say it is, in other words, is the arc length from a comma f of a, if you talk about points, to x comma f of x.
Are we doing f of t or f of x?
So that's a good question. F is a function. You can feed it whatever you want, as long as you're inside the, in this case, the interval a to b, because we're continuous a to b. So I can feed whatever I want. I can't, if I use x out here, outside of the integral, then I don't want to use x inside the integral. So I need what's called a dummy variable. We know after we take the antiderivative t, you're going to plug in these values for t. So t will stop existing at the very end when you plug your values in. So t is what we call a dummy variable right here. I could really use any letter that I wanted to. T is the standard one. You saw with a natural log of t, we went from, I think, 1 to x. 1 over t dt was the natural log of x. We use it. It was dummy variable t right there. So we're doing something really similar here. So I need just another variable that is not x, because we have x out here already. So I can still talk about x comma f of x, because in this case, I mean, you can just think about what's happening here. This curve's going along. We got a comma f of a. This is, we'll call this b comma f of b. And then x is some value in between a and b. So let's just say x is maybe right here. So this point will be x comma f of x. At some point along the curve between a and b. So we're getting in this case, the arc length of part of the curve. So not the full arc length, but the arc length of this portion of the curve. We can move x around if we want to. So s of x is the arc length function. So we're going to find the derivative of s of x, which is the integral a to x square root 1 plus f prime t squared dt. This derivative is super easy if you know what you're doing. Who knows what they're doing and can tell me the derivative? I don't even know anything about f prime of t at all. Well, it needs to be continuous, but be any continuous function.
Just cancel the antiderivative.
Yep, so derivative is going to cancel the antiderivative. What about the endpoints of the integral? Are they perfectly set up for fundamental theorem? Constant on the bottom, x on the top. So we're good to go. We don't have to switch endpoints or do any funky chain rule or anything like that. So this is just basically derivative cancels antiderivative. The other thing that happens, you do get f prime, but now it's f prime of x squared. So where there was a t, you're going to use the letter x, and a variable x in there. So this is the first fundamental theorem right here of calculus. Derivative cancels integral. Sometimes it is better to write dy over dx instead of f prime. So we could write that instead. And then ds. So this is ds over dx, so we have ds over dx equals square root 1 plus dy over dx squared, and if we multiply by dx, we can get ds equals square root 1 plus dy over dx squared, and then outside dx. What's your question?
Never mind, just on the earlier one, I want size. squared is part of that 1 plus 3y.
No, it should just be the second term squared. Yeah, the like, differential part of this is for the squared part. And I'm doing this so I can distribute dx squared inside the square root right here. So this is square root. Now we can distribute this inside here, dx squared plus dy squared. So there's a lot of different notations that aren't terribly important for us at this time. Mainly what you need is, what do we say? S of x is the arc length function, so I will put a box around the original S of x that we wrote right there. So that's what we really need off of this page. And this is called the GT arc length function. So we'll do one last example in this section. Find S of x, the arc length function, for our second example, which was y equals x cubed over 12 plus 1 over x from 1 comma 13/12 to, so last time we went from a number 4 comma 67/12, but now we're going to go to x comma, let's see, I'll call this the f of x, so the x comma f of x. All right, find S of x for this function. So we need derivative. So what is f prime? Take derivative. 3 over 12 is 1/4. X squared over 4 minus 1 over x squared. Yep. All right, S of x. Write down, just copy down what S of x is. Integral a to b. Square root 1 plus f prime t squared dt. Ooh, that's not right. What's wrong about what I just wrote down for S of x? Yeah, it should be x up there. Okay, so that should be S of x. Alright, try to do that fancy algebra without looking back at how we did it last time. So this pretty much came down to algebra. So we got to square f prime first. So there's f prime of x right there. So f prime t is t squared over 4 minus 1 over t squared. So I need f prime t squared now. So square it out. Do not do the freshman's dream, which is squaring each part individually. You get the outside-inside term also. Yeah, the outside-inside. So FOIL it out, reduce it down. pretty much as big exercise in algebra. I probably took derivatives into bad form, or antiderivatives. You probably want to write power, negative powers. I try to do it all in my head, which is dangerous if you don't have 17 people checking your work. If there's only you checking your work, I would not recommend doing these moves right here. So I was thinking t to the -2, add 1, which is t to the -1st, so that's 1 over t. And then I just basically did guess and check. What's derivative of 1 over t? Oh, it's -1 over t squared. Oh, so I'll just take care of that by making it negative. So it would become positive. All right, guessing and checking, really good tool. You can guess and check on a t cubed over 12 is derivative t squared over the 3 reduced to the 12 to a 4th. So you can go guess and check on that as well. That is s of x. It is sort of coincidental that this s of x looks a whole lot like the original. Not exactly like the original, but pretty similar to the original. That's coincidental. They won't generally look so much like that. It's so similar. Chances are if you take a derivative, square it, add 1, take the square root, and then antiderivative, you generally won't get what you started with. The reason I think that process works in general. That was just very coincidental that it worked out here. I mean, yes, you are taking, at some point you're taking a derivative, and at the end you're taking antiderivative, but because of what you do in between, don't expect it to come out to be so similar as this one is. This one worked out because from that funky algebra that we saw earlier, which is written down somewhere with A's and B's. There it is. That algebra property right there in the middle of the screen. That was why this problem was chosen. Most of them won't be lined up like that. So that is the end for arc length. Arc length overall, not terribly complicated. If I give you an arc length question on the midterm, you should be pretty happy. There's not very much to do. Take derivative, square it, add 1, square root, integrate. Don't have to take measurements, think about big minus small. There's none of that difficult part in these. So how do we make it difficult? We're going to take arc length and we're going to rotate it. And it's going to turn into a surface of revolution. So that's going to make arc length feel very similar to finding a volume in a revolution. So that is our next section. So this is 6.4, surface area. Surface area. So we'll start out with some pictures. So let's start out with a curve, kind of like we started all the other ones. Alright, so we just learned about arc length. So if I wanted to get arc length, I would break it into a bunch of small pieces, and they would be line segments. So let's use blue for the approximation here. I probably should have put some more curvature into this than I did. So it's going to look something like that. So let's focus in on one of these segments right here. I want to have a lot more curvature on here, so let's start over. It's going to look pretty similar. There we go. So break it into 4 pieces here. I wanted it so the segments are definitely distinct from the curve. The one I drew, the segments are so close to the curve. This one is pretty obvious that the segments are not the same as the curve. So we're just going to pick a segment. We'll just take the second one right here. So we're going to focus on this segment right here. So make that one super bold. We're going to rotate about the x-axis. So when we rotate, what shape will we get? Let's extend our axis some more over here. So I'm just going to redraw our segment and then do my best to rotate it around. And you get this shape right here. This looks kind of like a dog bowl that's not unspillable. This is not solid anymore though. So that's important to keep in mind. It's not a solid object because we didn't rotate the rectangle or the two-dimensional shape here. We rotated the one-dimensional line segment. So this is just a surface right here. This is not a full, not a solid object. So this is a two-dimensional surface. So this is not a three-dimensional solid, which is absolutely what it was in 6.1 and 6.2. When we were doing volumes, we were looking at three-dimensional solids. So we got surfaces now. So now we have to figure out what is the area, the surface area of this funky shape right here. And I'm going to do that very carefully. So if you look at it, it's basically not quite a cone, but it's like a portion of the surface area of a cone. So that would be one way to go about it, is to kind of extend it to a cone and then actually subtract like the full cone minus the piece that's not actually here. That would be one way to get the surface area. What we're going to do instead is think about what happens if I made this right here will be delta x. What happens if I shrink delta x more and more and more? It's going to make this line segment a whole lot shorter. It's going to stay pretty steep. It's going to stay the same steepness, but it's going to get a lot shorter. So what we're going to do is, because it will get shorter, we're going to, let's redraw it if it was super short. So I'll just look at the first little tiny part right there. So just make it just that much right there. It's going to make the picture look really ugly. I can't draw that well. So feel free to draw better. I just wanted to basically, if we were going from this x value to this x value, I just want to cut it off. Just go from the first x value just over a tiny bit. So we're going to get this shape right here. So what I need is this is pretty close to a cylinder. So I basically need a height and I need a radius. So this is going to be very close to a cylinder if I cut up small enough. We're going to measure the height in a slightly weird way though. So let's do the radius first. That's the one that makes sense, easy to see, and all that. So we're going to go with the radius right there. Now, why did I choose the left side? Why did I not choose the right side? Because if I cut these up small enough, the left side and the right side are going to be pretty close. So if I cut this into 1,000 pieces, the left side and right side would be pretty close. Of course, I need to cut it not just 1,000 pieces, but I need to cut it into an infinitely small, infinite number of pieces. So the idea is if I cut it up small enough, the left radius and the right radius would be pretty close. So I think you can see in the second version right here, they're a lot closer. And if I cut it up 10 times smaller, it would be very close. So we're not going to make a big fuss about which radius to choose. You cut them up small enough and it's okay. Now, normally I would measure the height with a measurement that would look like this right here. That's how we measured before when we were doing volumes. We're going to do something a little bit different here for surface area. And this is the only tricky part. We're not going to take this measurement parallel with the x-axis. What we're going to do instead is we're going to use the actual segment length right here. So that diagonal measurement is what we're going to use for the height right there. So this is what you can think of as the height. It's kind of slanted a little bit. So this is the height of our cylinder right there. And you should be thinking, well, if you cut them out small enough, isn't it really close to a cylinder? Think about cutting this into a piece that's 10 times smaller. Does that angle really change right there? No, it's still going to be, it's still not going to be flat, is the idea. So this measurement right here is never actually going to be parallel with the x-axis, no matter how small you cut it. It's always going to keep that, whatever the kind of curve, whatever the, in this case, right here, it's going to have that steepness, no matter what, no matter how small you cut it. So we're kind of stuck picking the height as this diagonal measurement. Good news is that is the length of the kth segment. So we have a nice formula for that height right there. So go back to the original pen and height, I'll call that L. So L is square root 1 plus f prime x squared. That's L. It is the length of that little segment right there. You flip back like 3 pages in your notes, we got this very carefully back there by using slope and f prime and doing some funky algebra. Okay, so how do I get the actual area now of this shape? So how do I get the surface area of this little slice? So we'll call this the kth slice. So our surface area is going to be, it's basically circumference multiplied by height. That's the way you do area of a cylinder. Just think of a can, a soup can. You want to know how big's a label, cut it off, you got a circumference measurement and the height. The only weird thing is our height is this L right here. That's the only difference. So it's going to be circumference times height, and our circumference 2 pi r. Our height, I'll write it as L originally, and L is this square root thing right here. So we have 2 pi r times square root 1 plus f prime x squared. So it's a little bit weird because we're not using the real height, we're using this sort of slanted height. So that's going to seem a little strange. All right, let's get a formula for R. The way that I drew it, R measures the distance from the x-axis to basically the point on the curve on the original over here. So if I come back with the blue marker, there's R right there. It's the distance from the rotation axis to our point on the curve. So if this is y equals f of x, our radius r is just f of x. It's how far you are above the x-axis. So how do we get the full surface area? We're just going to integrate each of these with a dx at the end from first x coordinate to last x coordinate. So we got a to b. So our full surface area let's see this. So I'm going to use SA for. Let's use S for surface area. So this SA right here is the surface area of one slice. Not to be confused with the full surface area, where we're going to integrate all the slices together. It's going to be 2 pi integral a to b f of x square root 1 plus f prime of x squared dx. Oh, make it. Oh yeah, class is pretty much over. Looks like we will make it. Good. All right, and we'll have a y version. Now there's an assumption I made on this picture right here. I assumed that our function was above the x-axis. So I better write that down. It's going to change things. If we're below the x-axis, r would be negative, and the part that would be messed up is that f of x would be negative. So this makes an assumption that f of x is greater than or equal to 0 on the interval a to b. So you got to be above the x-axis. If you're if you were below the x-axis, you could actually just throw an absolute value around the f of x right here. Would be one way to fix it.